applications and the web. Matthias?
Thank you, Andrew, for the warm welcome. Yes, I'm going to present the work of my group at Google on-device ML solutions for mobile and web. What do we mean by an on-device ML solution? Well, it's basically to run ML inference locally on device, as well as all the other non-ML building blocks that you need to achieve the required end-to-end functionality. And that's what we call a solution. Usually in on-device ML, we target real-time, low latency use cases because it unlocks a variety of new applications. For example, AR effects, like in Snapchat and Instagram, or virtual try-on, as you see on the right here in YouTube. Smart framing as part of computational video, like you've seen on the Nest or the Portal devices, real-time translation on the Pixel, and then, of course, the emerging use case of interactivity and triggers, which I'll show you a little bit later. On-device ML is connection-free, so you get your results immediately. That is obviously cost-efficient because you don't need to pay for data, as well as for a server. All the computation is happening on the user's device, which is also beloved by mobile developers because you don't have to maintain now an additional service. Instead, you just call an API like for any other functionality. And users have the benefit that it's inherently privacy conscious because all video and audio is analyzed on device. So this sounds great, but of course there are some technical challenges here. The first one is that mobile is severely limited really in the compute, memory, and bandwidth that you have available. But of course, we know that increasing capacity of models is really one of the key building blocks to achieve better quality. And so we need to be able to run higher capacity models. That means investing in faster inference. On device, you also have a fairly diverse hardware landscape, in particular on Android, with variety of different manufacturers of the SoC, and then you have a variety of different compute blocks on the SoC as well, and they vary in their compute profiles. For example, CPUs tend to have fewer fairly high performance cores, and then GPUs tend to have many cores but comparably lower performance. And so it's clear that different ops get accelerated in a different fashion. And so what you need to do is really target the hardware in your acceleration as well as in your models. You really need to tailor them towards CPU, GPU, or TPU for best performance. And then, as I mentioned, it's not just the model inference. You really need to look at the whole end-to-end pipeline, and you need to ensure that you get the best performance across ML as well as non-ML building blocks. So just to recap, the main building blocks for on-device are lightweight on-device models, specifically tailored to hardware, a solutions framework that really can do end-to-end acceleration across ML and non-ML, and then as well investing in ML inference, for example, TF-Lite GPU or XNNPAC, who's driving on-device CPU inference. Those will not be part of this talk today for time reasons. So what we will be focusing on are a variety of proven on-device models. Then I'll quickly touch on MediaPipe, our ML solution framework. And then we deep dive in 2 ML solutions specifically developed for AR here at Google. Let's start with the on-device models. I'll touch base on MediaPipe models. They're all open source and available to developers. Segmentation, FaceMesh, hand tracking, 3D pose tracking, as well as object and camera tracking. All have in common that they follow 5 core recipes for on-device applied machine learning. The first one is that we are leveraging ML pipelines of tightly coupled task-specific models versus one giant model. You'll see that we use it very often to implement tracking logic. And the advantage is, because you can couple the models, the subsequent models can really depend on the output of the previous one, and that allows us to reduce augmentations. In turn, we have more capacity, and it leads to better predictions. We also reduce the outputs. So for example, we favor regression over heat map approaches, which is kind of required as you increase the number of predicted points. And then probably one of the key ingredients is invest in good domain-specific data, high quality, have consistent annotations, very little label noise in the end of the day, and then run, an iteration across model training, as well as sourcing any data for hard negatives, annotating those, and keep iterating here. And then in the last is how do we unlock 3D, usually by leveraging parametric models or synthetic data that is directly fit to the real world ground truth. Okay, let's check in on a variety of models. The first one is MediaPipe Segmentation. This is our model that powers live viewfinder segmentation across Meet, YouTube, Duo, and Pixel. The real difficulty really is that in a video application, we have a dense prediction task. We need to do this in a sustained manner over many, many minutes. And so this requires low resolution, lightweight models that are kind of power efficient, right? While still reaching high quality. On mobile, we tend to use TF-Lite GPU to accelerate the model. On the web, we use CPU inference via XNMPeg. The way it works is it's a pretty straightforward UNet architecture, but with more recent or modern mobile backbones like MobileNet v3 or EfficientNet Lite. We use channel-wise attention to basically weight channels based on importance. And then here you see a variety of, or at least two different model complexities. This is the number of scan lines. So you see overall we have relatively few flops that will allow us to run it in the browser, but we achieve still pretty good quality when it comes to the intersection over union. The next model I want to touch base on is MediaPipe FaceMesh, which predicts 468 3D points from an image and basically powers all of Face AR across Google, YouTube, AR Ads, and Duo. And so the challenge here really is how do we predict the approximate face geometry of a human without the use of dedicated hardware. At over 400 points, of course, you can't have a heat map approach. It would be way too many output layers. And then use cases like AR makeup really require you to do high fidelity tracking of important regions like lips and eyes. The way it's implemented is it's a MediaPipe pipeline that consists of two models. The first one is a BlazePose detector that localizes the face in the image and gives you an oriented region of interest. And then we crop and we run a 3D mesh network afterwards that regresses over the 468 models. The nice thing of architecting it in a pipeline is you only need to run the face detector on the first frame or when the mesh network indicates that there is a tracking error. So the first model, as I said, is BlazePose, which allows you to localize faces in less than 1 millisecond. It powers basically all the FaceMesh applications at Google, as well as Duo auto framing. It's available to developers in MediaPipe as well as in TFJS, and the developer response has been really positive. On the FaceMesh side, as I said, after you run BlazePose and you get the oriented region of interest, we basically have two different capacities or even more with a common encoder to then predict 3D coordinates or the presence of a face. This flag is used to trigger the detector again. This is exactly the tight coupling. So the interesting challenge on the FaceMesh is really how do we arrive at high fidelity landmarks. Okay, the GIF is now loaded. And so what we do here is we follow a bootstrap approach where we train an initial model from just 2D contours and synthetic data. And then we really run a training loop over several months where we bootstrap annotations on unseen images. We have annotators basically verify on kind of like how far the ground truth is that prediction. If it's not too far, it gets refined, added to the pool of annotated data. We train a new model and we run this pipeline a variety of times. The performance that we achieve as measured by the interocular distance, that is the distance between your pupils, is actually similar to that of human performance, so really high quality. And then, as I mentioned, it comes in a variety of capacities and resolutions, all of them well within real time and on device. The next model I want to highlight is MediaPipe Hands. MediaPipe Hands predicts 21 3D key points per hand, also available in MediaPipe and TFGS. And the challenge here really is that it's a pretty naughty, difficult problem. Number one, when it comes to hand tracking, you have a huge variety of scale. Hands tend to be highly occluded, number one by themselves, but also, for example, with the face. They lack contrast compared to face detection, of course. And then, you just have this high variability, in particular in use cases like gestures or sign language that you need to be able to model. It also is modeled as a MediaPipe pipeline. You see the same building blocks here. So it's a palm detector localizing a region of interest, crop, and then produce the hand landmarks afterwards, and only run the detector when necessary. So why are we using a palm detector? The reason is palms are rigid. You don't have any articulated fingers. They're also fairly small, so you can still use non-max suppression to tell them apart, even during partial occlusions. They're roughly square. That means we can use fewer anchors. And then overall, we use feature pyramid networks as well as focal loss from retina net that helps with localizing hands across a large variety of scales. The hand landmark model also follows the design of the FaceMesh. The interesting bit that I want to highlight is really the two data sets that we're using to train it, real world as well as synthetic data. When it comes to the real world data, we use a set of human annotators to manually annotate key points in a variety of image. And then on the synthetic side, which will unlock 3D, we use a synthetic model, over 100,000 of renderers on realistic backgrounds to basically map it to the same topology and derive a 3D coordinate. So the applications here are quite interesting. Number one, you can predict gestures directly from the landmarks. You don't need to train a per gesture model that operates on RGB, so it's really scalable. And then there are two quite interesting applications that the community developed with MediaPipe Hands that I like to highlight. The first one is Miro, which allows you to control a prosthetis with MediaPipe simply by tracking your hand on mobile and then controlling the prosthetis. A very nice application. And similar is Neurons Lab that provides drone control via gestures. So here you see the hand is being tracked with the smartphone, and then over here you can give commands to the drone, and this is how it looks on the viewfinder. Okay, next model is 3D pose tracking. This is called BlazePose GHUM, which really provides beyond state-of-the-art quality on device with 33 3D key points available again in MKit MediaPipe TFGS. Compared to other approaches, it does localize hand and feet location, so you don't just get the wrist, which is important. Optionally, you can get a segmentation mask, and then it's really trained on data that also helps it scale to complex use cases like yoga, dance, and fitness. So as I said, the topology is 33 key points. It extends the classical COCO topology by these yellow additional points on hand, feet, and face. One of the nice features of BlazePose GHUM is that it produces actually 3D key points. The GIF should load momentarily. And that makes it one of the very few solutions that provides that on device. The advantage of having a 3D key point model is, of course, that you can do semantic analysis, like for gestures we had on hands, here for poses, because they're view invariant. Otherwise, you have to untangle this 3D to 2D projection problem. And it is built by using Google's 3D parametric human shape model, also called GHUM, that provides metric scale. BlazePose is modeled, again, as a MediaPipe pipeline, a detector, crop, and then the pose landmarks. The slight tweak here is on the crop. What you can see is it does so by virtual key points, 2 in particular. And we do that so that we have consistency between the detector as well as with the prediction model, which also predicts those 2D landmarks for center, as you see here, and then another point we can use to derive scale and rotation. Now, one of the challenges on pose 3D ground truth in comparison to faces is that synthetic data tends not to be realistic enough today yet to be usable by itself. So you really have a domain gap there, in particular when it comes to fitness or yoga poses. And then the lab setup, in contrast, has the issues that also has a domain gap because it doesn't cover the full variability of the real world. And so what we're doing is we're fitting a statistical body model, GHUM, to our 2D real world data. And of course, that has the challenge that you have an ambiguity. You know, there's many points that 3D points that map to the same 2D point. In particular, one issue is, for example, if I have my hand in front or behind me, yes, there is a scale variability, but per point, there might be very little change. And so annotators to untangle that are also annotating the depth order between pairs of joints or pairs of points in particular. So is a point in front or behind another point? And we only do this where an annotator can actually derive it. And that really helps with the 3D reconstruction. As I mentioned, BlazePose achieves state-of-the-art quality as evaluated on 3 different use cases. Now, taking all of these models that I've shown so far and putting them together, that gives you MediaPipe Holistic that we launched half a year ago, which really combines the face, hand, and pose models to produce a 540 key point 3D model in real time, on device, a variety of applications that are enabled by it. And it's really multiple models chained together with MediaPipe. So you have the pose model to seed it. And then because we have the landmarks for hand and feet, we can basically crop. We have models that slightly update the crop again to minimize augmentation and then regress over the remaining points on hands as well as face. So the application that this enables, pretty cutting edge, are quite nice. And you can try them out as well on our webpage. So for example, you can touch your face for particular triggers. And then you can also track your hand with respect to your body. That gives you a 2D coordinate system where you can basically sit on the couch and then have something like a virtual keyboard. Quite interesting. Community built also some solutions with it. KaleidoFace is probably the most known for live 3D avatar tracking. So you really see from the webcam stream pose, face, as well as hands are tracked. And so as you see, there is motion in the fingers here. The last model I want to highlight is MediaPipe Box Tracking. This is a classical computer vision approach that allows you to track any 2D region via sparse optical flow. I'm going to skip about the details and just show the use cases. It is used in Google to track regions of interest in Google Lens, these little gleams that you see, or live translations in Google Translate. In the second part of the talk, I know we're running a lot of time, but I'll wrap up soon. I want to touch base on MediaPipe, which is our ML solution framework, open sourced and also widely used across Google products and research to build ML solutions. Basically allows you to build ML pipelines from reusable building blocks. Is really optimized for analyzing time series of data. And then it provides you with this vital end-to-end hardware acceleration across and ML and non-ML for really great performance. So you see a lot of the models and solutions that are highlighted are available in MediaPipe across Android, iOS, desktop, C++, Python directly, call it in Colab, and JavaScript to run it on the web. I'm going to skip the concepts for time and just going to touch base on some of the ML solutions that we built for AR over the years. The first one are live AR effects in Google Meet. We released this last year. In particular, we worked on background blur and replace, as well as low light adjustment. The interesting capability here is it runs directly locally in the web browser. There is no native app required, and it's powered by MediaPipe, C++ code that gets cross-compiled to WebAssembly to be run in the browser. And so it's one of the only solutions that actually gives you rich ML models that can also run on, for example, Chromebooks that don't even support native apps. So the way this is designed is as a web ML pipeline. The building blocks, as I mentioned, are a MediaPipe solution cross-compiled to WebAssembly, and then also cutting-edge ML inference in the browser via XNNPAC that is leveraging the Nesson-Wasm SIMD standard. So this is the ML solution where the browser passes in the video texture. We do all the analysis and rendering in MediaPipe, and then we show the result back in the browser. It is a segmentation model that I initially described, as well as WebGL-based rendering for really a refined result. And so the rendering that we're doing is for the background blur, we use a non-uniform blur, in particular around the edges to minimize halos. And then for background replace, we use the common Photoshop technique light wrap to blend the background a little bit into the foreground and reduce this like soft pixel boundary and give you a more realistic effect. You can also accelerate the CPU model by using sparsity. Here the idea is weights that are close to zero. You just push them to zero. You don't need to compute them. Of course, the inference engine needs to be optimized for it. XNNPAC is, in particular when it comes to sparse one-by-one convolutions. And all in all, the model gets a quarter faster and is also a quarter smaller, which makes a big difference, for example, on a low-end Chromebook.
Matthias, you got about a minute left.
Yes, I'll wrap up. Another feature that we launched is low light mode, where the idea is to fix imbalanced exposure by analyzing the foreground only. I'm going to skip about the details and just show you the results. So really runs in the browser. It was launched this September and brightens the foreground subject. Okay, and then the last bit that I just want to show is the live AR effects that are running in YouTube and Duo. And here the building block is really the combination of BlazePace and FaceMesh, computing blend shapes. It's a 3D face geometry to set up the OpenGL renderer, and then basically have a renderer to drive all of the AR effects in the native app. And with that, I can take maybe one question or at the panel discussion later.